Hi. We're having massive technical difficulties today, as you might have expected. Hey, can you grab my charger?
Sure. Where is it?
It's plugged into that wall. Sorry, today's live stream is coming to you from my laptop, not from a desktop. It's too late. You're already on.
I'm the assistant.
I have two assistants today. There's a fur dog down on the floor, and Boo. Welcome to GenChem. This is not ideal. I don't know what happened to my other computer. This is my house. So I'm glad you're here. Hopefully this will not be a routine issue. Welcome to class. So the way this will work is down on my screen. It's over on this side, but it might be on that side. Somewhere there's a comment box that if you have a question during the lecture or anything else, you can ask. Lily is here, just hanging out on the ground. So a couple of things. Welcome to class. 2. Computer wasn't charging. We were going to have a rough day. So a couple of things. Your exam 2 scores were posted in Canvas, so you can look at those there. So your scores are up. The key is up. In the first COVID-19 announcement I gave you guys, I said, hey, I'd be happy to scan those. So 2 things happened after that. 1, they closed the university and sent all the faculty home. As you can see, this is my house. And 2, I don't own a scanner. So as soon as the university opens, I will get in there. I will scan them all. I did find a way how to do it easier. Unfortunately, I figured out about that after they sent us all home. So I don't really know what happened. It just got crazy. So that happened. There were some other announcements that I have for you. Hold on that. I will post the usual announcement slide on Canvas. So today we're going to try to finish out chapter 6, which we will do on this whiteboard. I'll also introduce you guys to the dog here in just a minute, if you haven't met her yet. So the other thing is we're going to end chapter 6 today, and then we're going to talk about periodic trends this week. Likely that will not encompass all from 3 to 4:15, both today and on Wednesday. So there's that. Quip 8 will happen. So we're going to try to stick as close to the previous syllabus as possible. So we're not making any changes yet. But I do want to be clear, there is a small chance that there will be lots of changes. Every day it feels like there is a new informational statement. We're just going to kind of roll with it. So we are going to have Quip 8 on Wednesday. For the life of me, there is not a good way how to get you guys to watch both of them at the same time. So what we will do instead is it opens at 4:15 on Wednesday, and you have until midnight to take it. It will be somewhat similar to the Quip that we did online before. 5 points if you give it a go. You have to write something in the box. Even if you write, Dr. Malcolm, I really don't know anything about this. So that's an option, not your best option, but it's a fine option. The topic is electron configuration, which is what we're going to talk about first here today. So we're going to do that. We're going to continue to use Alex. So if you don't attend live school, you have 2 options. 1, you're probably not here. But you can watch live school. This class will go to my YouTube channel. It will be in the chapter 7 where there's some examples. Your Alex homework is still going to be due Thursdays and Mondays. Right now, those are the plans that the university has made. So we're going to do that. That will be due on Thursday. The exam 2 key is up. My office hours are at the normal times. They're in Zoom. So it's a little different than the way Megan's doing SI Zoom. So the way this works, on the homepage or in either of the announcements that I sent you, you can click on, there's a link that says, I think, unf.zoom-Hannah Malcolm. If you click on that, it will take you to a Zoom meeting. As far as I know, you have two options. You can download Zoom to your device, phone, tablet, and that will work. So it will work best if you have a camera, mostly so that I can see you. You can, if you do not have access to a phone, 1-800 number that I will post up there so you can call that as well. When you go into that, I'll try to leave a sign if I've like run out to get some water, but it just sits open on my computer so you can come there. If you bring some work to do, we can basically do problems together. We're gonna all experience this non-face-to-face learning together. And this is not awesome because frankly, I'm super sad that I didn't know that 10 days ago was our last time together. So, but that's okay. Hopefully the school will open back up and you guys can come back by my office later. So everything else will be the same. Does anyone have any questions before we talk about chapter 6? I need more coffee. Even though I'm talking fast, I'd like to apologize. But to be honest, I'm kind of nervous. And I don't know if it's my complex or the neighbors who are doing, hold on. Somebody's doing lawn care, so I'm really sorry about that. The objectives are due on Thursday, and I think there's 3 or 4 objectives. It's pretty much 3 or 4 for the rest of the semester. So, sounds like you guys can hear me. Now, you'll have to see this. So, class will be exciting today. I'm gonna use this whiteboard, and there's my pup. I know it's a little dizzy. We have someone who asked, Zoom is for office hours. That is correct. So this is a good question. There's 2 different Zoom links. So on Canvas, there is a Zoom like button. If you click that button, it will take you to SI. If you choose not to do that, I think Megan can send a link out. She and I will get together to do that. On the front page for the course in Canvas, I changed it to where it says they're held in Zoom. You can just click that button and that will work. Correction, that is supposed to work. So since for whatever reason I brought home my work computer, which decided today of all the days to no longer believe in opening up YouTube. It was the strangest thing. Not gonna lie, it was a massive crisis, but we're here now. We are gonna do stuff. Oh, Megan gave an announcement that she will provide you with all 3 Zoom links. Ooh, if you are in Central Time Zone, I do believe that yes, they will be turned in at 3 Eastern, but I will double check that it is not. I'm not gonna lie, this comment box is working way better than I had expected. I do not know if SI requires you to have a microphone or a webcam. I believe you can just watch. You may end up signing in a slightly different manner, but you still should be able to show up. You will just not have any audio input. And you guys can see the comments. Megan says that she thinks you can just watch and she will email you the worked out worksheet solutions if necessary. Whoa. Hold on, let's close a few things so that maybe there are less alerts. But I'm gonna go with probably not. So, okay. I am gonna follow the PowerPoints We will try to get you guys a blank worksheet for SI. I will talk to Megan about that. I am going to pull up, so I have a laptop open, and then behind me is the slides. So I'm going to start today's lecture in chapter 6 on slide 51, which is titled Electron Configurations, because two computers, two excitement. We ended right before exam 2 talking about quantum numbers, and now we're going to talk about when we have an atom, where does it go? Like, where do the electrons in oxygen or anything else live? So if you have a periodic table, great. If you don't, for all of our online assignments, I will try to post one or a link. All right, I made my chair go way too soon. I did because I think it's possible you guys went home for the holidays. My gosh, God, I'm so sorry. I do know how to fix this. We are starting at 6.8. I did find an online free textbook for those of you if you do not own a textbook. So, periodic table. I'm going to try to lecture now. We're doing great. I'm going to take my glasses off for now. Are you really going to sleep right there? I hope you guys can see. It's not great. Let me close the blinds. So, okay, let's think about what we're going to do today. So, hi, honey. My pup is starting to wake up. I'll get her to stand up in a few minutes so she can say hi. So today we're going to start in section 6.8. So we have all these electrons, and we know that the electrons are in specific orbitals. And so we talked about how the electrons are in 2 per seat, and we talked. So let's go back in time and think about, where do our electrons live? So we know that they live in orbitals. So electrons they live in an orbital. And hi, honey. There's my dog's cute little tail. She's adorable. You're fine. You can sleep. So we know that they live in an orbital, and we know that they have n, which is our principal quantum number. And then we have L, which is the orbital. And then M sub L, which is our subshell or our suborbital. And then we have M sub S, which tells us about the directionality. And so we know that for any, you can't see that at all. Hold on, let me get a new marker. Hey, where do you think you're going? Come here, love. Come on. Here, come here. Come on, up. Come here. Sorry, my dog is pretending that this is the worst day of her life. So we know that they all live here. And so I know you can't really see it, but it says that there's an N principal quantum number and an L orbital. So we could say that it's in the 1s. That makes it slightly better to see. Hopefully that light gives you a little bit better visual. What is the SOB? The 1s orbital is the, so We know that n equals 1. Thanks. Suborbital. So a suborbital is, if we think about the p orbital, we have px, py, and pz. And so we know that there are 3 different versions of that orbital. And so if we were to think about this, like our electrons get on a yellow bus, you know, like the kind, obviously I went to school, elementary school in the 90s. And so we took a school bus, and so 2 students sit in each seat. So we know that m sub s gives us their directionality. We have 1 up and 1 down. And so the p orbitals, there are 3 different flavors, for lack of a better term, in this case. So today what we want to think about is, where do the electrons go? If we know that they have them, where do they live? Are you going to stand up the whole time? Apparently. So when we think about orbitals, so if we have lithium, we know that lithium has 3 electrons. And so it turns out that with electrons, watch out, Lil, watch your toes. That's a little bit better. It's not my best work. We'll work on it for next time. So lithium has 3 electrons, and so those 3 electrons all need to have a specific seat. And so when we think about those, they go in order. And so the thing is, orbitals have kind of like a filling of seats. So if we were to file single file into a space, you can basically go into one place versus another place. So for lithium, it turns out that there's the 1s orbital and then the 2s orbital. So if you remember back to quantum numbers, we know that for n equals 1, whoa, it can have an L equals 0. These are the, you can't see that, which is the s orbital. For n equals 2, we have L equals 0 and L equals 1. So we have an s and a p orbital. Good, we can mostly see that. So the quantum numbers tell us about the order. Shortly, definitely before the end of class, one of the things we're going to do is we're going to learn that there's a pattern, kind of like everything else. So someone asked, how do we know it has 3 electrons? It's a great question. So if you look at a periodic table, the atomic number in your periodic table, this is your periodic table square, where we have 3 Li, and then it weighs 6 point. Awesome. My life I was about to pronounce this is super. So in your periodic table squares, there are a couple of things. This first one here, so the number 3 is the atomic number, which is either the number of electrons or the number of protons. Li is the symbol, and this 6.941 is the mass number. So those 3 things together tell you about this. So for all of the elements in the periodic table, we can see how many electrons they have, as long as they're not charged. Good question. So we have our 3 electrons, and we know that we go 1 up, because we know that the N, L, M sub L are the same for any pair of electrons. We have 1 up and 1 down. Kind of like choosing which ones you like. You may put up first or down first, depending on how you feel. So there are 3 in this way. So for lithium, we have 1 up, 1 down, 1 up. So the thing is, for the s orbitals, there's just one option. When we start to think about p orbitals, so if we look at, in this case, we're going to think about nitrogen. So nitrogen has 5 electrons. And so, no, it doesn't. Nitrogen has 7 electrons. It's not my day. So nitrogen has 7 electrons. And so when we think about this, we know that there are 7. What we are starting to think about is that the orbitals go in order. And so when they go up, we start with 1s and then 2s and then 2p. We learn that from the quantum numbers where they go from n equals 1 to n equals, we're going to learn on a periodic table is 7. And then we have L 0, 1, 2, 3. And so we really only have S, P, D, and F orbitals in the periodic table today. So for nitrogen, we have the 1s, the 2s, and the 2p orbital. So when we add electrons, one of the questions is, do we put all of them in the first, second, or the third? So when we thought about lithium, the s orbital only holds 2 electrons. So we put 2 in the first one and had 1 left over. So there are 7 electrons here. So the second slide today, slide 52, says Hund's rule. So degenerate orbitals this just means the same energy. So when we think about a degenerate orbital with maintaining the same energy, it just means that the 3 of them are all at the same place. And so we can see orbitals 1, 2, and 3. So 10 electrons because it has a -3 charge. If it had a -3 charge, it would have 10 electrons. But in this case, we're talking about nitrogen just by itself. And so it doesn't have a charge. So without a charge, it is the number in the periodic table. It's a great question. So in here, let me grab we're going to try a red marker. And if this doesn't work, we'll go back to black only. So when we think about these 7 electrons, ooh, yeah, you can see that, I think. So when we add them in, each orbital gets totally filled before we move to the next. So we'll add 2 electrons to the first one, 2 electrons to the second one. So we've used 4 of our electrons, but there are 3 left. So the question becomes, where do they go? Do we put 1 in each P, or do we put 2 in the first one and 1 in the second one? So it turns out for degenerate orbitals, these are p orbitals or d orbitals or f orbitals, where you have more than 1, px, py, pz, etc. In this case, those 3 orbitals, we can then put 1 electron in each one. Now you'll notice that as I drew them in, they pointed up. So we know that I'm going to answer that question in just 1 second. So we put them all going up so that they have parallel spins. So Sarah asked, how do I know that the 2p has 3 spots? It's a good question. If we think about the quantum number L, we know that the m sub L equals -1, 0, and 1, which we also talked about how that equaled, there were S, PX, PY, and PZ. So these 3 things here tell us that 3 orbital. So for L equals 2, which is the S, P, D, F orbital, we know that the m sub L values are -2 to 2. So there would be 5 different distinct orbitals. So in that case, this will make more sense. As we kind of build this together, it'll start to clip together kind of like a Lego. I think we're going to find out. So when we add the electrons, Hund's rule, hold on, let's go back to a black marker. The red's a little bit hard to see. So Hund's rule basically states for degenerate orbitals, the lowest energy is for parallel seats. Now, I like to think about this if you and I all get on a yellow school bus. Usually, unless your school bus driver had rules, mine did not. The way we got on the bus was 1 person per seat. You kind of sat in the middle, you had lots of space. And eventually people started filling up 2 by 2. But really no one does that until all of the single seats are full. So Hund's rule basically says what we as people know. we would rather sit in the seat by ourselves for as long as humanly possible. So Hund's rule basically states that we set them up here, here, and here. And in this case, we can kind of look at them in this way. So when we continue to kind of think about this, we're going to begin to start to look at where do all the electrons go. So there are a couple of definitions that we need to think about. So when we think about a nucleus, if we have any atom, we're going to have what we're going to call core and valence electrons. So core electrons are any orbital that is fully filled, or we're going to say any shell. So any shell of electrons that is fully formed. So any shell of electrons. Now, right now, I know that you're like, I don't know what you're talking about. That's okay. It's okay to be like, how does this process with what we know? Right now, we just know that the electrons go in seats. So basically what I'm saying is, if you go to Disney, which I haven't been in ages, maybe when this is all over, I'll go. But one thing I do vaguely remember is that a lot of times they would make people fill up one tram card before you could get on the next one. So that first fully filled car is called the core electrons because they're fully filled. The valence electrons would be that next one. Yes, Kaylee is correct. This is kind of a class. Welcome to school. So in this case, any shell of electrons that is fully formed. So a valence electrons is what is on the outside. So the valence electrons basically kind of attach when we make bonds in chapter 8, which is what we're going to talk about next week, that will only be the valence electrons. So valence electrons are basically the things that do cool stuff. This is the outer exterior of our atoms. So when we think about all of these different things, our goal is to figure out where the electrons go. So when we think about different electrons, so if we think about any of our elements, so we're going to kind of work through some different ones. One of the things that we know is that our orbitals go in this order. We have a 1s, then we have a 2s, and a 2p. So this would be n equals 1, L equals 0. So the quantum numbers that we learned, what feels like 900 years ago, if you vaguely remember those, tell us how many orbitals there are. So we have 1s, 2s, 2p, 3p. From here, it's going to get a little confusing. So next, we'll talk about 4s and then 3d. Hang tight on the questions as to why these two aren't together. We will get to that. So when we look at this, the thing with electrons is we just fill them together. Every seat, if it's degenerate, we fill them one at a time, and then we go back in and add the rest. Or we fill any s orbital all the way through every way. So as we think about this, we can look at, let's say, beryllium, boron. We did nitrogen a little earlier, so we'll look at neon. Good, and there'll be plenty of space, and we'll look at sodium. Are you just sleeping? Sorry, my dog is like sighing like this. I wish you guys could see her. We'll work on that for next time. So when we think about beryllium, boron, neon, or sodium, so let's think about, the first thing is, how many electrons do we have? That's your first question. For all of these, they're going to start in the same spots. We're going to basically draw the same series of lines. So electron configuration can be drawn or written. We're mostly going to do online communication, so we're mostly going to write it. But sometimes we need to know how to draw it. So for beryllium, when we look at our periodic table, which is right here, we can see that beryllium has 4 electrons. So boron has 5, neon's going to have 8, and sodium will have 11. So if we are asked to draw our electron configuration, we have 1s, 2s, 2p. To know how many electrons this holds, we just count them up by 2. 2, 4, 6, 8, 10. So if we have 10 electrons, all of these will be full. So to draw these, we just go in and add our electrons counting. So 1 electron, this can only hold 2, so we go 1 up, 1 down. For the 2s, we go 1 up, 1 down. We've now used all 4 of our possible electrons for beryllium. So this would be a final answer. The 2p orbitals can be included, but are not required. If you have all of them, then that would, so if you do not have to show this if there aren't any electrons that live in there. If you wanted to write this, thanks for the catch on neon. I don't want to say I'm a mess, but I'm not a mess. So for beryllium, there are 4 electrons. And if you wanted to write it, it is a big number 1, the letter S, 2. So this number right here, so this over here is drawing. Now we're going to write. So we have the 1s and this superscript 2. That number just tells you that this orbital has 2 electrons in it. So whatever it is, you just put that at the top. So there's 1s2, and then there's 2s2. So now we can write out our electron configuration. So let's think about boron, which now has 5 electrons. We have the 1s, 2s, 2p. So when we add our 5 electrons, we add 1, 2, 3, 4. Now this 5th one needs to go in a p orbital, but I'm going to put it in the first one. So I put it in the first one because I felt like it. You could put it in the first one, in the second one, or the third one. You could put it downside if you would like. So this last electron can be in any of these, because if you remember back to the quantum numbers, you can put it in any of these that you like. So I put it in the first one. I only put it in the bucket. You could put it in the middle one. You could put it in the last one. You could put it in any of these upside down. So that would be like this. So electrons tend to be single barbed arrows. Likely if Alex asks you, I'm sorry, to do that, then you would just set it up in that way. So it's gonna get a little, oh, we gotta write those out. So if you were to write this out, it would be 1s, 2, 2s, 2, 2p1. So this 1, which is quite small, sorry, tells you that for the p orbitals, there's only 1 electron in there. Would you be required to write the exponent? Yes. So the exponent for this over here, this just tells you how many electrons are in there. So if they're missing, so if I'm going to write this big over here. So we have 1s, 2s, 2p1. So you can be asked to go, using this information, identify an electron or identify an atom that has these electrons. So the exponents tell you how many electrons are in any of those components. So the written is, we're gonna leave that comment alone. We'll figure out how to kick people out if that becomes a problem. So these exponents tell you how many electrons are in any of these. If you go from left to right in the periodic table. Yes, we'll talk about how to read the periodic table in just a second. So let's see. If we think about, let's look at sodium. I'm going to erase this stuff up here. And we're going to move up. So now let's look at neon, which has 10 electrons. So we have the 1s, the 2s, the 2p. So when we add these electrons, ooh, thank you for blocking someone. Ooh, on Alex, the exponents range from 1 to 10. So Sebastian has a question about the exponents range from 1 to 10. So you can have up to 10 electrons in an orbital. The p orbital can hold 6. Sorry, that person can peace out, Cub Scout. So in here, we put our electrons in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons here. For the p orbital, it can hold up to 6. So in this case, if you write it out, it would be 1s, 2, 2s, 2, 2p, 6. So earlier, we kind of talked about the core electrons, which are over here. And these are our valence electrons. So whatever the largest big number, so anything that is fully filled over here on the left, over here it is slightly different. Why is it that we stop at 2p? So Amanda's asking, why do we stop at 2p? Thus far, we haven't had any elements that go beyond 2p. In just a second, we'll look at sodium and then potassium. And so both of those will have more than just the 2p electrons. I like the comments. This is, to be honest, this is working almost as fantastic as I had imagined. Really, the downside is it's very hot. So for sodium, we have 11 electrons, and for potassium, we have 19. These numbers I'm mostly writing up here so you guys can kind of think about it. If we know that this is the order that they're going to go into, we could sit down. I will do sodium, and then I will give you guys a second to think about and give potassium a go on your own. So for sodium, we know that we're going to have 11 electrons, 1s, 2s, 2p, 3s. So we could go ahead and draw the 3p, but I do know that in this case, this will be the last one that we need. Yes, if there is an element like sodium where it has an additional electron, we keep going further. So we'll plop in our 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So for sodium, let me get a blue marker. These elements here, or these electrons, this is our core. So the core electrons are separate from the valence electrons. So the reason we think about the core is this part is kind of like the apple core. We put it in the center, and I don't particularly eat those. So the core electrons live in the center. And so one way that we can write a shorthand, because sodium just has 11 electrons. But if we thought about something at the bottom of the periodic table, like rubidium, that has a lot more, and so it can get tedious trying to write all this out by hand. So it turns out that we can use the core and the valence in order to come up with a shorthand. You know how much we chemists love how much this is. Don't torture our visitors, guys. So we can write it in a shorthand. Now you might be like, whoa, what just happened? So I basically said that this core looks just like neon. If you look back in your notes, or in the non-live version, you can rewind a little bit. The neon looks just like this. So we can use the closest noble gas core and then just write the valence electrons or anything after that. So in this case, we have neon and 3s1. So I'm gonna give you guys a second. If you have questions, go ahead and ask them. To write up the potassium ones. So we have the 1s orbital, 2s, 2p, 3s, 3d, and the 4s orbitals. So 4s, hold up, this is the 3p orbital. I got excited. So I will check the questions, make sure I'm asking any of these. So for Amanda, who asked about neon, that is correct. For Sebastian's question, you can, for the exams, it would specify, it will say you can use noble gas configuration, which would be this right here, or you cannot use noble gas configuration, in which case you would write out the long way. And for sodium, it would be 1s2, 2s2, 2p6, 3s1. So this would be the long way. This would be the noble gas configuration. So for no. I think we had a momentary blip. So yes, it's argon 4s1, and it is one behind. So the way you can kind of think about that is it's the noble gas that you encounter along the way, as opposed to the one before, or the one further down the row, because we can't take credit or get things that we don't have yet. It is the one before. So for sodium, it will be neon because we will encounter that along the way. For things like oxygen, it can't be neon. It would have to be helium. So let's think about potassium. So we have 19 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So for those of you who said it was argon, 4s1, for S1. That is totally correct. So you could write it all the way out, or you could do shorthand. You can also, if it asks, set up a shorthand with the drawing of the electron orbitals, where you just put argon and then 4s1 with a single electron. So the way we know it is argon, this is probably not the best way to do this, but I don't really have another way. So this is a terrible plan, but we're going to roll with it. So the way that we know it's argon is because as we travel across, we encounter argon before we get to potassium. So the noble gas configuration is a shorthand. And so it's always the noble gas in the row above the element of in question. So it would be the last full shell. So it usually ends with any of these noble gases over here on the, all the way to the right side of your periodic table. If the noble gas configuration confuses you, you don't have to use it. It is an optional shortcut. So a couple of things as we start to think about, okay, so reading periodic table, the first two columns is S. Yes, Sarah, you are slightly ahead, and we're about to get there about how you can read the periodic table and make it easier. But as usual, we kind of have to get a little up the mountain before we can make it easy. So what Sarah's saying is there are patterns in the periodic table, which we know is our friend. So I'm going to draw my periodic table up here. Yes. So when we look at our periodic table, which this is only mildly to scale, but that's okay. We know that we have different things. So the noble gases are over here on the left. The right. Let's just go with this side. Hooey. We have our noble gases over here all the way on the side. And so these two columns over here on the left, these are our, you still can't see that. These are the S. Anything in this column will end with S1. No, I do not have a Nintendo Switch docking station because I don't own a Nintendo Switch. To be asked about the F, unlikely. Mostly we'll stick with the S, P, D, and orbitals, and very rarely will we encounter the F. So here on the left are our S. These are our P orbitals. This here, our no rules kids transition metals, are the D orbitals. And down here at the bottom are F orbitals. So if you get confused about how many electrons sit in any of these regions, you can actually just count as you go across. 1, 2, 3, 4, 5, 6, 7, 8. So most of the time, the electron configuration Aaron, I'll answer your question about exams in just a minute. But short answer, I have no clue. I think we're going to do them online. I don't know yet. Right now, all I can tell you is our QUIP is on Wednesday and it's online. But it's a good question. I wish I had a better answer. So if the d orbitals holds 10 for any element in here, you can count all the way across. So elements in the d, p, and f orbitals all follow Hund's rule, where you count and fill. These would be a d5. It goes all the way across. So someone earlier asked about exponents up to 10. That was probably for a d orbital on there. Michael asks, the quip is due at the end of the live stream. Well, neither. Quips are due, it opens right after class at 4:15, and you have until midnight in case you have to run off to go somewhere else, you know, to your next class or something. I don't know. But also to give you guys less time so that you're not stuck in front of a computer for days and days. So for P, D, and F orbitals, we look at them like this. So if you slide up to, if you're looking at the slide 55 and 56, both show you this image. And so all this is to say that they work in this order. So a couple of different things to kind of think about these type of options. Most of the time they go in order. So it turns out that there are a handful of no rules kids. Now, like everything in chemistry, there are no rules kids. We've met them before. They're often in the d orbitals. That is not going to be different in electron configuration. So how do we know who doesn't follow the rules? So we'll do examples at the very end. If you if you go to slide 58, which we all have to look at those. I'm in the chapter 6 handouts. It's at the very end. It has some hot pink squares on top of the different options that don't follow the rules. So it turns out that anybody in the F orbitals that doesn't follow the rules, I will never ask about because they don't follow the rules in a pattern. So we're going to erase these and just let them go away. So it turns out that the S and D orbitals, and we're going to think about elements like chromium, which is element 24, and copper. So with the 4s, 3d, in this case, the reason they fill outside of the normal rules, let's think about chromium. And so it has 5 valence electrons. Ordinarily, we would put 2 in the S, and it contains 4. 1, 2, 3, 4. Ordinarily, we have 2 S and these 4 in the D. So from here, the reason it doesn't follow the rules, and I'm sorry about my internet's having a meltdown. It keeps telling me it's lagging. I'm so sorry. We want to move this electron here and flip it to where it looks like this, because this puts 1 electron in every seat instead of 2 electrons in one and having an empty seat here. If we think about our bus analogy from before, each of these would prefer to be in a single seat if at all possible. So the only other thing I've got to tell you, so far we've talked about the different order, but the 4s is filled before yes, Vanessa, you can borrow an electron from the S to completely fill the D. So we can do that to move 1 into the D, or for things like copper, you can move, actually palladium can move both of the S into the D orbitals. But some of you might be wondering, okay, Dr. Malcolm, you said that we go in order, and 4 is before 3. For S3D. For Sebastian's question, it would be 4s and then whatever the exponent is, in this case 4s1, and then 3d5 in the noble gas configuration. If you were asking whether or not they need to be 4s1, 3d5 versus 3d5, 4s1, I do not care, but Alex, I feel like, has a very particular statement on that. So the only other thing I want to think about today, and then I will give you guys some examples and answer any questions out of the comments box. So there's two things that we kind of want to think about. Oh, I just erased my periodic table, which would have been helpful. So I'm going to put that back up there. If you look at your periodic table, all the way over here on the left side, there are 7 rows, right? 1, 2, 3, 4, 5, 6, 7. These right here tell you about the s orbitals, which you cannot read that at all, but okay. So these numbers here tell you the n shells, which also tell you the large numbers for anything else. So we read left to right the same way you do in a book usually, right? So there are patterns in the order in which these are filled. So yeah, y'all can see this. Sorry. 5p. So when we draw these, Ronnie, you are always welcome to come to class. We meet here on Mondays and Wednesdays at 3. So in here, if we draw diagonal arrows in this direction, it tells us the order in which we fill these orbitals. So we fill the 1s, then the 2s, then the 2p, 3s, 3d, 4s. Then we'll go back and fill the 3d, 4p, 5s. And I will try to draw this and upload a picture onto Canvas with the chapter 6 notes so that we can look at that. Are there earlier lectures? There are some earlier lectures for other information, but not for the rest of chapter 6. So we can put these in order. So for the No Rules Kids transition metals, the first row is the 3D, 4D, 5D, 6D, and the F orbitals are the 4F, 5F. So these just are downshifted. These are a little off-shifted as well. For an exam or something else, a lot of times I've watched students draw this first as well as label them in this way. So 4, 6. I'm going to write up some Yahtzees. Elements. Let's look at, they're on slide 57 and 59 have multiple questions. So I'll write up some elements. So let's see, we have chlorine, phosphorus, we'll have molybdenum, and what's another one off of this one? Yikes. Ag. Okay. Now I'm going to come over here and I will work on those in just a second. I want to check my questions. Kaylee is correct. At this point, now, I'm going to be honest. I have not I haven't checked my email since class started, so a billion things could have changed. But when I thought we were going to be online for 2 weeks, I thought that worksheets would be helpful. We're going to at least try this for the week, which today I feel like went pretty well, where I lecture using this super tiny whiteboard and I have the slides pulled up behind. In that case, that information is available. So I I opted not to do the chapter worksheets because it felt like I was trying to do too much and you guys are busy. Ooh, thanks for the comment. I think this worked pretty well. So there are no more worksheets, but the worksheets that were online for all of the other chapters are available to you. So you have those. If you guys need more example problems, I see a request for step-by-step examples and a link for the textbook. There are examples for, I think for this, I will double check, and if I need to, I can upload some more since I don't get to see you guys as often. There are lots of examples already for many of these topics that we're going to cover. And the textbook link, I can post that. So Jesse asks, are we changing the class to pass-fail design or it stays the same? When we started class at 3, there'd been no statements about whether or not UNF was going to pass-fail. I do know that a number of institutions have gone to pass-fail. We will do what UNF does. And I don't know. So right now, we're going to try to stay as close to the syllabus as possible. We will be running our exams and quips through Canvas. Although I did hear that Alex offers online exams, so we might give that a try. But since we just had exam 2 and we have several weeks to figure out what the best practice for exam 3 and the final, I figured that we would try to solve all of these problems and go from there. Let's see, other questions. The Respondus Lockdown browser is not for quips. To be honest, there aren't a lot of great methods, and I told most of my friends that it feels like they kind of threw us in hot water and we're trying to figure out how to swim. Quips will just run through Canvas the normal way. They are open book, open notes. So you know what? Let's just make it work. For the exams, they will likely be open notes. There will be a couple of things that will change. I don't know. I can answer questions about exam 3 or the final, mostly because I haven't gotten there yet. It says it's reconnecting. Okay, sorry. I think it glitches in and out. I'm really sorry about that. For chlorine, it is neon 3p5. I agree that the answers are hard to find online, so we'll probably do something else. Exams are open. We will figure out all of the exams as we move along. Ooh, good catch, Megan, that it is 3s2, 3p5. So someone asked for chlorine that it would be I'm answering your question about 3s2. So for chlorine, it contains 17 electrons. So we have the 1s, 2s, 2p, 3s, 3p. So when we count in our 17, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. The 3s, which is a little hard to see due to the computer glare, these are the core. So these 10 electrons are accounted 4 in neon. So it's neon 3s to 3p5. Good, you guys can still see that. So the neon, the noble gas has to end with a p orbital. And so from here to here, you encounter the s orbitals, as someone said. Yes, you do have to go backwards. You guys are doing great. This is coming along. On Wednesday, we will start chapter 7. We're only going to do, section 7.1, 2, 3, 4, and 5. At the end of the chapter, we're not going to talk about that. We're not even going to read it. We're not going to look at it at all. We're just going to do the first several sections, which are on periodic trends. Does anyone else have any other questions before I don't want to say run off to go to my next class, but the usual. If you're just tuning in or missed the earlier announcements, Lil will be here every time. I am not currently on the schedule to teach Chem 2, but I teach biochem, so you can hang out and take me again then. The QUIP is on Wednesday. It's over this stuff. It will be a writing, the electron configuration, which is the stuff like this. It will not use noble gas configuration. So it will be over that. There's no way to do the arrows on Canvas. It's just too crazy. So you have a QUIP on Wednesday. That is correct about phosphorus. We have that. And if you would like to come to office hours tonight, you can click the Zoom meeting. I will be there at 5:45. Otherwise, I will see you all on Wednesday. Have a fantastic rest of your Monday. I miss you all very much. Bye. Oh, wait. We have a few questions. It's not that yet. We will not be using noble gas configurations. It will always say that in the questions. Stay healthy, you guys. Try to get in your fitness steps. I'm going for a long walk with the dog tonight.